Hi! So we're here now to research about the latest optical materials. To understand optical materials, we first define what is optics. Optics is the branch of physics which involves the behavior and properties of light, including its interaction with matter and the construction of instruments that use or detect it. Relating optics to materials, an optical material is a material which is transparent to light or to infrared, ultraviolet, or X-ray radiation, such as glass, and certain single crystals, polycrystalline materials, and plastics. One interesting topic about optical materials is this video about camouflage.
Camouflage can be the difference between a soldier getting shot and going home. So a lot's riding on the next generation designed to outfit troops. It's only been 8 years since the Army spent $5 billion on camo that critics say didn't fool anyone. Soldiers complained to the point the Army abandoned its one-size-fits-all universal pattern.
So they were looking for camouflage that they could use everywhere.
Correct. And it didn't work anywhere.
Guy Kramer is one of the designers competing to win the Army's next multi-million-dollar contract. This summer, he showed us the science behind every shape, size, and shade of these pixels.
You now have your camouflage. So we're trying to trick the brain into seeing things that aren't actually there.
Digital patterns recreate shapes already found in nature, and 3D layering creates depth and shadows where none exist. That's today's design, but developers already have one eye on tomorrow.
What's coming up down the road and very quickly is the Harry Potter cloak.
What is it?
With that fictional cloak, Harry isn't just camouflaged, he's invisible.
My body's gone.
How invisible are we talking here? If I walked into a room with a soldier wearing one of these cloaks?
You wouldn't see him at all. He would be completely invisible to you.
This isn't make-believe. The military has seen the so-called quantum stealth technology. It works by bending the light around an object, even concealing most of a person's shadow. Imagine what that could do for a sniper hiding in a field, or the American pilots who ejected over Libya when their fighter jets crashed last year.
They could actually pull out, very similar to what they carry with a survival blanket, throw it over top of them, and unless you walked right into them, you wouldn't know that they were there.
So what was once firmly in the world of make-believe could quickly become quite real. The science is in the special fabric, so you don't need a power source or some instruction manual to make it work. Theoretically, any soldier, even in the most remote location, could quickly put it on and get it working.
That is really interesting topic. I think a lot will benefit from it. Going on to a new optical material which is, I think, is commonly used nowadays, which is the fiber optic cable. Did you know that researchers have now developed a new fiber optic technology capable of transferring data at a rate of 255 terabits per second, more data than the total flowing traffic across the internet at peak time. To understand how fiber optic cable, we will now watch this video.
I find this a fascinating object. It's a fiber optic cable for a stereo. If I shine this laser pointer down the cable, it guides the light out the other end. These cables are used to connect our world today and are capable of transmitting information across countries and oceans. But first, let me show you how it works. I have a bucket that I've modified with a window in front. And on the other side, I put a stopper in this hole right here. I have a bottle of propylene glycol with just a little bit of creamer in it. A ring stand. And of course, a laser pointer. Now, keep your eye on this plug when I turn out the lights. That's wonderful. The light follows the liquid flow all the way to the bucket. Amazing. It does this because of total internal reflection. As the light enters the stream, it is reflected as soon as it hits the interface between air and liquid. You can see here the first reflection, and then the second, and the third. This occurs because there's a difference between the index of refraction of the guide material, here propylene glycol, and the outside, air in this case. Recall that any time light strikes a surface, it can either be absorbed by the material, reflected from it, or pass into and through it. The latter we call refraction. It's easier to see from a top view. Reflection and refraction can happen at the same time, but if a light ray hits the surface at an angle greater than the critical angle, it will be completely reflected and not refracted. For this propylene glycol and air system, as long as a beam hits the surface at an angle greater than 44.35 degrees, measured from the normal, it will propagate down the stream via total internal reflection. To create this same effect in an optical fiber, engineers create a core of glass, usually pure silicon dioxide, and an outside layer called cladding, which they also typically make from silicon dioxide, but with bits of boron or germanium to decrease its index of refraction. A 1% difference is enough to make a fiber work. To make such a long, thin piece of glass, engineers heat a large glass preform. Its center is the pure core glass and the outside the cladding. They then draw or pull a fiber by winding the melt onto a wheel at speeds up to 1,600 meters per second. Typically, these drawing towers are several stories tall. The height allows the fiber to cool before being wound onto it.
Did you know that one of the greatest engineering achievements was the first ocean-spanning fiber optic cable called TAT-8? It extended from Tuckerton, New Jersey, following the ocean floor over 3,500 miles until branching out to England and France. Engineers designed the cable to carefully survive on the ocean floor. See how optical materials can improve our technology to a higher level. So that's all for our research about optical materials. Thank you and goodbye.